Hello and welcome to the first virtual OCP Summit 2020. My name is Rizul Altin-Kilic, Project Manager for Global IT Key Accounts and working for Ital, and Tim Schecht, Director Product Management for ZutaCore. Tim and I would like to show you a new cooling solution for today's and upcoming data centers in combination with the OCP technology, rear-door heat exchanger, and direct chip cooling.
Liquid cooling has always been one of those exotic technologies of the future. But now, we ask Alexa what we should wear today. We ask Siri to translate an important request into Mandarin. Our vehicles keep us in the lane and stop us at that intersection with the hidden stop sign. They find the path with the least traffic and update it continuously. We can now predict dangerous storms and weather with unprecedented accuracy, allowing those affected to prepare and seek shelter. Medical computing can now detect tumors that humans cannot, and assist in the search for treatments to dangerous or rare diseases. We take most of these things for granted now, but they are enabled by increasingly dense computing. We now regularly see processors that dissipate 200, 300, and even 400 watts. This makes for very power-dense servers. But these servers often need to communicate with other servers at high speeds, requiring a lot of high-powered servers in a rack. This increases power density in the rack. And when a lot of computation is needed, that density extends to the data center. Although we can cool high-powered servers with air, the cost to do so goes up exponentially with power density. So, intense computing applications and the high-powered computers that support them all point to liquid cooling as a technology of today, not the far-off future.
The main challenge in many existing data centers are the demand of increasing computing and chip power, and also rack densities. But they don't have the current infrastructure to provide water to racks or to the cooling units. The road for this solution is quite simple. Cool the heat source and don't take too much computing footprint away for cooling. Ital and ZutaCore are using a non-conductive liquid for direct chip cooling. It's a two-phase closed-loop system with low pressure, and the cooling can be used on demand. On the right side, you can see how it works. The liquid is going through the evaporator, what we call ENE. There it's getting evaporated. The vapor is flowing back through the manifold into the air-cooled condenser. There it's getting liquidized again.
At the heart of the system is the evaporator. The evaporator removes heat from the processors by boiling the dielectric liquid from the enhanced surface. Boiling is so efficient that a flow of just 140 milliliters per minute will remove 400 watts of heat from a processor. The base of the evaporator is enhanced to enable very rapid and effective boiling. Hence, it is named the Enhanced Nucleation Evaporator. This device replaces the air-cooled finned heatsink that would normally be used. As can be seen, it is very compact and can be designed to fit any processor socket. Because it uses so little fluid to remove a lot of heat, the inlet tube is only 4 millimeters in outer diameter, while the outlet tube is 6 millimeters in diameter. Of course, the evaporator can't do the job by itself. The evaporators placed in parallel on all of the processors in the rack efficiently collect the heat. Small 6 millimeter tubes direct the vapor from the processors to the refrigerant distribution unit, or manifold, which then passes the vapor to the heat rejection unit, or HRU. The HRU contains fans that blow cold aisle air across a condenser, forcing the refrigerant vapor to give up its heat and condense back to a liquid. A pump then draws that liquid out and pushes it back to the evaporators, where the cycle begins again.
As you can see in the picture, the solution can be adapted into the OpenRack version 2, what is on my left side, or into the OpenRack version 3, what is on the right side on the presentation, without modifying any infrastructure in your data center. No water connection is needed, as mentioned before, and the cooling medium is a non-conductive liquid. On the left side, you can see the OpenRack version 2 in the presentation. It's on the middle side. You can see the OCP version 2 with the 6U heat rejection unit, we call that HRU, the manifold in the back, what is near located to the bus bar, and the NEs sitting on the CPUs and GPUs. On the left side on the presentation, you can see the OpenRack version 3 with the rear-door heat exchanger. I would like to give you more information about the rear-door heat exchanger. In the bottom area of the door are the pumps and the liquid tank located. The liquid is getting pumped through the ENE and through the manifold and going inside of the rack and going back to the door again. The rear-door heat exchanger for the OCP V3 rack has a total cooling capacity of 55 kW and the airflow rate of approximately 3,000 till 8,000 cubic meter an hour. The inlet temperature is 30 degrees Celsius and a maximum outlet temperature of 46 degrees Celsius. The most important thing is, no matter what the load is, the liquid stays constant about 50 degrees Celsius. I would like to also call for action. On the link tab, you can see how to get involved into the OCP working group rear-door heat exchanger. There is a bi-weekly call. You can join it by clicking the link. And also you can find the latest specification of the working group OCP Advanced Cooling Solution rear-door heat exchanger. Thanks for joining and stay healthy.
Hello, this is Tim Shedd. If anyone has questions they want to ask.
Okay, I can see a question from Atkinson Tran. He asked, okay, what size of the fans are currently? I mean, as you know, we are aiming to, let's say, provide the rear-door heat exchanger on the OCP rack V3, and it has more or less, the rack is more or less like 600 watt, and the fan is slightly smaller than 600, something like 400.
You can think of this as having fans typical for an active rear door. So there are actually a number of different arrangements, and currently we're looking at the wider fans, as Razul just mentioned. So another question we had was, how do we compensate for back pressure? So that's a part of the design. As you know, the saturation temperature at the NEs is controlled in part by the pressure of the system. And so an integral part of the design is designing the network, the fluid network, so that there is minimal back pressure on the NEs to maintain low pressures at the evaporators. The connectors used are quick connects, currently a model by Parker, to be honest, but there are a number of different quick connects that can work because the flow rates through the system are very low. So there's a lot of flexibility on quick connects. Razul, feel free to jump in. Again, this is Tim Shedd. There's a question, how is two-phase viewed by integrators? Actually, there's a great deal of interest from integrators. There are a number of applications in which, whether it's performance, thermal resistance at the chips, to a desire to investigate options that don't include water in the rack. There's a number of reasons why integrators are very interested. As far as the QDs being specific, the only requirement really is to be careful with the O-ring materials inside the QDs and any lubricant that's used on the O-rings. And this can be done in collaboration with the Quick Connect suppliers and 3M supplier of the fluid. The pressure drop in the system, not sure off the top of my head. It's not very large, and in that it does not significantly affect the boiling point at the ENEs, but that's a good question. I don't have that information. On the liquid side, actually, we don't worry so much about that because the liquid is fed to the ENEs, and only enough liquid is fed to the ENEs as is needed. There's actually a valve that controls the fluid flow so that there's not actually, generally speaking, continuous flow of liquid to the ENEs. It's Don Fernandez from Facebook, who was part of the previous presentation, is inviting you to participate, inviting all of us to participate in the door heat exchanger specification, so that we all have an agreement on the size and the specifications of the door heat exchanger. So Nicolay, I don't understand your question. That way we pay for vertical density, 2 is minimum height, 1 is impossible. I don't understand your question. We can certainly implement this technology in 1U servers and have frequently, actually. So we can enable 4 processors in 1U, for instance, without any problem. So advantages compared with water glycol is that one of the most direct advantages is just the fact that it's not water. If it does leak, there is no damage to the components. The other is that the flow rates are much, much smaller than typically a water-driven system has. So the tubing is very small, 4 millimeters OD and 6 millimeters OD on the outlet, and very flexible. So it allows for incorporation into a number of different geometries without having to really be overly concerned with the plumbing internal to the server. The heat rejection heat exchangers also tend to be smaller because they are condensers rather than radiators. So they tend to be more efficient, exchanging more heat per volume than a water-cooled heat exchanger typically. The fluid does not ever need to be treated. You don't need to worry about corrosion or biological buildup or anything like this. So that's another huge advantage. And to lead into Shlomo's question, the system is designed so that it does not need to be recharged at all frequently. It can be as little as once every 5 years. More frequently if there's a lot of servers added and removed from the system. And there's a very simple an inexpensive pump apparatus that makes that process very simple and easy to do. So there's very little Novec in the rack. Typically, it's a very, very small cost to the system. And the amount of liquid that permeates or leaves the system over time is small because there's actually relatively little exposure to polymer tubes. There are polymer tubes we've demonstrated, but the amount of area for permeation is small. Thank you all for your questions.
Coming to the question too from Rayesh, he was asking, okay, what is the additional cooling requirement to the system fan power? I mean, it depends, let's say, absolutely on the configuration, but in our case, the fans has a cooling, or let's say the rear door heat exchanger, and also the fans has a capacity of 20 kW in this case.
Thank you. I actually missed some questions. I apologize. Related, is there any loss of Novec during operation? No, it's a closed system. It is meant to be somewhat like your refrigerator in your kitchen, just completely cycles the fluid around. The pump, a number of different pumps can be used. The initial pumps in the products that are available now are rotary vane pumps. And yes, there's careful design, and part of the intellectual property of the system is maintaining a liquid state at the pump inlet. So on connectors price, we have several great connector suppliers participating in OCP. I'm sure they'd be happy to discuss this with you, Shlomo. Some contradiction. Low pressure involves danger of explosion. High pressure in PUE decreases in 95% of the time. So I'm not aware of an explosive or explosion risk. The fluid we use, Novec 7000, is non-flammable. And there's, to my knowledge, no risk of this. The system is designed, of course, so that if it does heat up and pressures do rise a bit, the pressures in the system typically are below 2-bar gauge. So I'm not aware of a pressure of an explosion risk. As far as pump reliability, the suppliers of the pump provide significant MTBF according to their data, and there's always N+1 redundancy on the pumps. So to our knowledge, the reliability should be good. We have the additional cooling that Razul just answered. Purging the air. So again, this is a pretty simple process. There's a small unit with a small vacuum pump that it takes, I've done this several times myself, it takes less than 5 minutes, and the initial installation and commissioning, and after that there's typically not a need for purging, unless again you add a number of servers all at once, and it's a simple, quick thing. Connectors on the cold plate. So these are actually push to connect, so they're very easy and fast fittings. Yeah, so again, the system operates at 2-bar gauge or less, so the fittings are not terribly sophisticated. And yes, Steve, you're right. The refrigerators do not have quick disconnects. However, quick disconnects are a reliable technology in hydraulic systems everywhere. I'll look up the pump name, but I don't have that off the top of my head. High volume usage. So environmental impact. So Novec 7000 is not the lowest GWP fluid, and as any responsible company, Rittal and Zudico are together investigating lower GWP fluids. However, the total amount of fluid involved is quite small, and it's unlikely that even that amount of fluid would be completely lost. So we're talking about 15 liters per rack on that order, and so it is anticipated that the environmental impact is small. So Ying, the surface enhancement is really interesting, and this is one of the key technology features of the system. So the heat exchanger itself is finned, as you have seen many times. Fins spaced about 1 millimeter apart, about 1 millimeter thick copper fins, and in between is a wicking material that is inserted between all the fins, and this material actually does two things. It wicks fluid down to the surface so that the fins are completely wetted at all times, as well as providing a really great enhanced nucleation surface. So every time this relatively rough material touches the copper surface, it creates a new nucleation site for boiling. Thus, the boiling starts at very, very low heat fluxes. Unlike when you're boiling water for spaghetti, you have to sit and wait for it to boil. The boiling is nearly instantaneous. And so again, this is part of the intellectual property of the system, but essentially the boiling enhancement is kind of standard copper fins with this wicking material that's inserted between each one. Razul has answered the GWP question. It's a medium one. And as per explosion risk for the 3M engineered fluids, again, I would refer you to 3M for discussions about that. They're experts and happy to work with anyone who has questions or issues, but they have not brought to our attention that we need to. Yeah, I'm sorry. You've noted there are no documented risks of explosion. Thank you. Yeah. Okay. Ying, have we considered a cold plate? Indeed, this is a type of cold plate, if you want to think of it that way. And again, it's designed specifically for very, very efficient boiling operation. So do you have to pump it down to a vacuum when you add remove a server? No, we do not. You can add a server, and as I mentioned earlier, there is a simple purging process. So it can actually work quite effectively with a fair amount of air in the system. It's not terribly sensitive to air in the system. But once, and there's a automatic sensor, and once the level of air in the system reaches a warning, a level of which it might impact the performance, a warning is triggered and sent out via the network or also on the front panel, and someone can go and purge the system easily and quickly. Jamil is on from 3M. Thank you, Jamil, for your response. Razul answered the internal volume of the rear door as about 10 liters. And thanks, Tejas. Good to see you. It's been a little while.
Okay, any further questions so far? Thanks, Luis. Thanks, Nikolai.
Thank you, Nikolai. Thank you, Ying. Thanks, Sean. Stay safe. Look forward to discussing with you all. Our contact information should be easily available. There are no other questions. We'll close this one out to let the next presenters go, but feel free to continue the discussion and reach out with any further questions. Thank you very much.
Thank you. Enjoy the summit.